Awesome. I don't want to keep you waiting, and we have quite some material to go over in the upcoming 30 minutes. So first of all, thank you for joining in the session. There's already a lot of folks joining in, so I like that. Even though it's a virtual UserCon, at least it's a live session, right? Kind of like that. Would be better to be in person as well, but hey, maybe next year. All right, so in this specific session, I want to talk to you about vSphere vMotion, one of my favorite features and capabilities within vSphere. And we did quite a lot with vSphere vMotion in vSphere 7, but also vSphere 7 Update 2. We introduced, in the patch release, we introduced the advanced cross-vCenter vMotion capability as well. So I really want to touch on all these topics in 30 minutes. So let's immediately get started. Really quick introduction. I'm Niels Hagoort. I live in the Netherlands, so pretty close by. And in my daily role, I am a tech marketing architect at VMware in the Cloud Platform Business Unit. So basically sitting in between engineering, product management, and customers and partners like yourself. All right, about vMotion. What we have done with vMotion over the years, because we introduced it in 2003 already, so it's been quite a while. But till this day, it is one of the greatest, one of the most momentous game changers in the IT industry, right? The ability to live migrate a virtual machine from one host to another host, even across data centers, and nowadays even across public clouds, even with VMware's cloud offerings across various platforms, it still baffles me. And it is a live migration that we are talking about, right? So there should be no impact to the actual workload itself. Now, in this specific session, obviously, we'll focus on what we have done in the latest releases, vSphere 7, where we introduced a lot of logic optimizations, and 7 Update 2, where we introduced the auto scaling of the streams. The streams initially introduced in vSphere 4.1 already, but there's definitely some significant changes on that part as well. So let's dig into it. The logic improvements are by far the greatest improvement that we did. And like with DRS, our beloved distributed resource scheduler, what we have seen is that data centers or infrastructures maybe are changing, right? And there's no exception with vSphere infrastructures as well. There's a lot of type of workloads nowadays. We used to have just your regular virtual machines, but nowadays we have these large database backends, right? We even have those monster, air quote, monster virtual machines. A lot of computational power assigned to only one virtual machine. We have machine learning, we have obviously containers with vSphere Tanzu. The vSphere is really the platform to host all of these workloads. But especially for the larger workloads, we have seen that customers weren't always comfortable using vMotion. And by not feeling comfortable using vMotion, they would set DRS to disabled or manual, right? Where we want customers and partners to experience the ease and the performance that it brings to enable DRS and feel comfortable using vMotion, doing live migrations, which makes life easier, right? Not only from a performance perspective, because we can balance across the cluster, but also from an operational point of view. If we want to do maintenance on our hosts, we want to be able to live migrate virtual machines off of a specific host, right? So we needed to refactor vMotion to make sure that its capabilities are also up to the task when we are running large workloads. So to give you an understanding of what we have done with vMotion, let's quickly touch upon the overall process, right? So whenever DRS in fully automated mode or we ourselves initiate a manual migration, what happens is that we create a ghost virtual machine on the destination ESXi host. We copy over all the memory. Once we have memory convergence, we'll suspend the virtual machine on the source. We'll transfer the device state and the last remaining memory pages, and we resume the virtual machine on the destination. Now, this switchover phase, this is what we refer to as a switchover phase or the stun time. That is what we would like to keep, we as a VMware, we would like to keep under 1 second for you, right? So whenever that happens, we have a successful migration. The workload is running on the destination ESX host, and we'll clean up everything on the source side as well. Looking a little bit closer into that process, whenever that migration is initiated, the vCenter server will start a long-running task, and it immediately does a compatibility check. Now, this is all about versioning the available resources, and this is key, not only to run the virtual machine on the chosen destination ESXi host, but also to support the vMotion process. And this fits into the stream architecture that we'll talk about in a later slide as well. So when that is done, a migration specification is created. Now, this is all about the virtual machine that is being live migrated, right? Its configuration, what is the source, what is the destination ESXi host, what are the details on the vMotion enabled network. Once that is all done, that migration specification is passed on through the virtual provisioning XDaemon, VPXD, which is the process in vCenter server, which communicates to all the ESXi hosts using VPXA, the agent equivalent. VPXA will reach out to host D. Host D is important in this specific process because it maintains the VM state, for example. So whenever a migration is initiated, host D will make sure that a virtual machine is set to an intermediate state so we can no longer change its configuration. Meaning if you hit edit settings, you won't be able to change anything for that specific virtual machine, which makes sense because it is in a live migration, right? So VMX is involved, VMX not the configuration file, but the process, and VMM. And VMM on the source is key because VMM, the virtual machine monitor process, that is in charge of the memory, basically, the memory pages that are in use by that specific virtual machine. VMX and VMM will reach out to the vMotion logic, the kernel module, the migration module. Sockets are opened on the vMotion network, and we'll start copying over that memory, right? Now, this is an iterative process. So what we'll do is we'll use multiple phases to copy over all of the memory pages. So in phase one, we copy over basically the entire stack of memory pages for that virtual machine. In this specific example, 24 gigs. Now, as we do so, the guest OS and the application running inside the virtual machine or container or whatever workload will obviously overwrite memory pages because it's a live migration, right? The application just keeps on running, OS keeps on running, guest OS keeps on running. So it dirties another 8 gig, meaning that 8 gig is being overwritten during our initial memory send. So we retransmit the dirty 8 gig. In that process, it dirties another 3 gig. We send over the 3 gig, it dirties 1 gig, and in the last phase, in this specific case, or a specific example, we have 3 phases, 4 phases, I mean, and we'll be able to reach memory convergence in those phases. If we need more than that, we'll obviously use more phases, right? More iterations. So on the back end, what happens? If a virtual machine or a guest OS and the application running inside of it tries to write to memory during a live migration, during a vMotion, VMM process set the local host memory to read only. And we do so to enforce a guest exit, meaning that we can now check what memory pages are being overwritten, basically, right? So VMM will, in the meantime, change memory on the local host from read-only to read-write, write to local host memory, but simultaneously call out the migration module, the vMotion logic, mark this page as dirty, and replicates that page on the over the vMotion network to the destination host. So this specific process is referred to as a page fire. And to understand what page fires are happening, we need to install a page tracer. Now, what we have done with vSphere 6, all the way to 6.7 update 3, and even versions before that, by the way, what happened is that we needed to stop all the vCPUs of that specific virtual machine to install that page tracer. Now, we're talking microseconds here, but still, especially when you have those monster virtual machines, this can cause a significant impact on the workload performance because we need to stop all the vCPUs of that specific virtual machine. And we need to do so to set the PTE, the page table entry, which is the memory, basically the memory pages, to read-only access, to enforce that guest exit we just talked about. And in the end, we need to flush the TLB as well. TLB being the translation look-aside buffer. Without going into too much detail, that is basically a caching mechanism for us to quickly understand what virtual page is what physical memory page. But the key is that we need to stop all the vCPUs. So in vSphere 7, what we have done is basically looked at that logic and said, what if we just claim one vCPU to do all the tracing work, while all the other vCPUs will just continue to do calculations, computations for that specific workload. By doing so, greatly reducing the performance on the performance impact on the workload already. So vCPU 1 will make sure that that vCPU is entitled to set all the page table entries to read-only. In the end, we do need to flush a TLB on a one-to-one relationship with the vCPUs, but we do so in different times. Basically, waiting for the CPU scheduler to have a little idle time in between context switches, for example. And again, we're talking microseconds here, right? But then we'll quickly flush the TLB so that has a less impact as well, right? So this is about what we are doing during the memory sendover, the memory copy, right? So one other thing that we have done is we've been talking about setting the page table entries, the memory pages to read only to enforce that guest exit, right, to VMM. Typically what we have done is set that read only flag on a 4 KB page table entry. In vSphere 7, however, we set it on a far larger granularity, namely 1 gig pages instead of 4 KB pages. Now, this is basically less work that we need to do, less work that the ESXi vMotion logic and VMM needs to do, because no longer do they need to go over all the 4 KB page table entries, rather than now having just to set the read-only flag on the 1 gig. So less work is less impact on the workload as well. This is everything from a memory copy perspective, the pre-copy iterative memory process. So when we look at the what happens in the switchover phase is basically that we stop with the memory pre-copy process like we just discussed, because we have reached memory convergence. And this, I quickly wanted to show you, this is happening to determine if we have a memory convergence on the destination ESXi host, right? Basically, it's a check of all the memory pages sequentially between the source and destination ESXi host. So we start at the page 0, the first page, memory page, and we check all the way to the last or max page, right? Now, VMM will check if we can terminate the pre-copy, the memory pre-copy process. And to do so, we check the migration tags, which consists of the migration transmit rate. So at what speed, what bandwidth, basically, are we transmitting memory pages to the destination ESXi host? The dirty page rate, which is at what pace is the workload itself, the guest OS, overriding memory pages as we are in a vMotion process. And we have the page count left for transmission. Basically, the dirty pages that we still need to send over and replicate over the vMotion network. And we do a calculation to see if the final iteration of this process fits in 500 milliseconds. 500 milliseconds because we still need to do some other things and we want to keep it within a second, right? So if the answer is no, we'll do another round until the answer is yes, and we move ahead to terminate the pre-copy process. Now we move over to the switchover process, where the stun time is involved, right? So like we said in the beginning, this is where we suspend the virtual machine on the source. We transfer the checkpoint data, which is basically all the information that the destination needs, the VMX process on the destination needs to basically boot up that virtual machine using the memory pages that we have just replicated. So it's sort of an interrupted boot process where the virtual machine, the ghost virtual machine, will be booted, pointed to the memory pages that we replicated instead of claiming new memory pages. Also, we transferred the changed bitmap. The bitmap you can see as a file that is, well, it's basically a file containing all the information of the memory pages in use of that specific virtual machine. So, and we need to send that over to the destination because the destination needs to know what memory pages we are talking about, right? If you overcommit memory, You might have a swap file as well. So we need to send over the swap bitmap as well. And to give you an idea of its sizes of the bitmap. So if you have a 1 gig virtual machine, you'll be talking about a 30 KB bitmap, right? Not an issue to send over in a couple of microseconds. Oh, milliseconds maybe. However, a corner case maybe, but today we do support virtual machines, one virtual machine with 24 terabyte of memory. And yes, we have customers running these configuration. Think about large SAP HANA or Epic database environments, for example. But you see the challenge here, right? Because we are all already talking to almost 800 megs of bitmap. So we transfer the last remaining pages, which the vMotion logic extracts from the bitmap. So we know what last memory pages that we need to push over to the destination ESXi host, and then we'll be able to do that interrupted boot process and resume the virtual machine. Now, this all happens within less than 1 second, ideally, right? That is what we are aiming for. So what we did in vSphere versions prior to vSphere 7 is that we send over the full bitmap. Now, the full bitmap consists of information about memory pages that we already have replicated to the destination ESXi host. So there's really no need for us to understand information about those memory pages on the source as well, right? So what we have done is to compact that bitmap to only include the information about the last remaining memory pages, basically, that we need to understand, so we can move those to the destination ESXi host. And using that same example of a 24 terabyte virtual machine, again, maybe a corner case, but you get the point, right? We go from seconds to send over that full bitmap to mere milliseconds, even for a 24 terabyte memory. So we cut the time really significantly, and by doing so, shortening the switch over phase as well. So what is the result of all of these improvements, right? So we have used a test bed with a HammerDB workload and just a regular sizing, I would argue, a 12 vCPU, 64 gigs of memory, already a pretty beefy virtual machine. But if you're talking about a database backend, this is pretty common, I would say. So we measure the commits per second over a 1 second time granularity. And what we'll see with vSphere 6.7, for example, is that we immediately notice when the vMotion operation is initiated, right? Because we see a drop in performance. Now, this drop is already 27% during that tracing phase that we talked about earlier on. Also, we notice when the vMotion ends, because we see a full drop to 0 commits per second. Good thing, though, is that we still remain within that 1 second of a switch over time. However, if we look at and compare that to a ESXi 7 environment, we don't necessarily see any impact during the tracing phase. More interestingly, maybe, is that we now have a shorter overall migration time. And the switchover is so fast that we don't even drop to 0 commits per second in this specific test. If you up the numbers of the computational numbers of that virtual machine, things will become even clearer as well. So same thing, 72 vCPUs and 512 gigs of memory. And what we see now is that we have that vMotion begin with already 66% drop of impact. And we see that switch over time with 6.7, which is already multiple seconds. With vSphere 7, we don't have any impact. And we see that we still remain within that 1 second for the switch over time. So that is how we made sure that customers can be more comfortable using vMotion, and by doing so, DRS as well in vSphere 7. Let's quickly hop over to what we have done with vSphere 7 update 2. And that is to make live migrations faster. So typically, without going in too much detail, whenever you have a VM kernel interface that you enable for vMotion, right? So just setting up your vMotion network, what happens is that we spin up a single stream for that specific VM kernel interface. So that consists of a completion helper, basically doing all the things we just discussed to help the vMotion process itself. So we need CPU cycles for that. If you do encrypted vMotion, you'll need the crypto helper, and we have the stream helper. The stream helper really is about claiming CPU time, CPU cycles to put the data on the wire to the destination ESXi host. Now, this hasn't been an issue really, right? It was more the other way around. So whenever we are using 1 gig or 10 gig NICs, we actually want to leverage multiple NICs or multiple physical NICs to create more bandwidth, basically for vMotion. So multi-NIC vMotion already helped. However, if we're looking in using 25 gigs or up, which is becoming mainstream quite quickly. So 25 gig, 40 gig, 50 gig, even 100 gig. We have a lot of customers looking and investing into that already. What will happen is, because we only have one stream helper, which can only saturate one full core, right? So by doing so, we might not be able to saturate that full 25 gig of bandwidth for vMotion. Now, we already have a lot of options to cope with it, right? One, you can add more VM kernel interfaces, because per VM kernel interface will spin up a single stream, right? So you already have multiple stream helpers to push out that bandwidth. We could also use some advanced settings for a single VM kernel interface enabled for vMotion and up the number of streams using those advanced settings. But in the end, that adds complexity and overhead, because especially with additional VM kernel interfaces, you might, you might not, you need multiple IP addresses. There's just a lot of operational overhead on that part. And in the end, it does what it does, right? We can span out multiple stream helpers so we can utilize multiple cores, and by doing so, saturate those high-speed bandwidth networks. However, what we want is optimal vMotion performance, but no manual tuning, like we just said, right? And we want it to scale automatically as well. So that is with vSphere 7 update 2, we introduced vMotion autoscale. So whenever you update to vSphere 7 update 2, you'll immediately start using this as well. However, if you already configured the advanced settings to up the number of streams per VM kernel interface, you need to revert that to the default setting to make sure that you will benefit from the new bits in vSphere 7 update 2. What we have seen on average, because it depends on CPU and network and other components, is that with the vMotion process, be able to spit out basically 15 gigs per vMotion stream. So that obviously for 25 gig will automatically spin up 2 streams to saturate 25 gig. With 40, we'll spin up 3 streams, and you get the point, right? Key takeaway is that no longer is manual tuning needed to fully saturate those high-speed bandwidth networks. Now we're quickly running out of time, but I definitely wanted to focus on this specific capability as well. And this is the advanced cross-vCenter vMotion capability, a mouthful. And we refer to it as a XVM capability. We're great with using abbreviations, I guess. I'm not sure. Anyhow, this was a really popular fling, right? This has been a fling since vSphere 6.0 update 3. That is where we first introduced the APIs in the vSphere stack to make use of this functionality. Now, you might not have noticed, but with the patch release of vSphere 7 update 1C, we introduced this in the vSphere client as well. So it's now completely embedded, and no longer do you necessarily have to set up that separate fling. Now, it is great for multiple reasons, but to give you a high-level overview, it is basically 2 workflows that we support with the advanced cross-vCenter vMotion capability. And that is that we can import from a vCenter server instance, or we can migrate to a vCenter server instance. Key takeaway here is that this is about vCenter server instances that run in completely different SSO domains, right? So there's no need to have link mode, either enhanced or hybrid link mode. And this opens up a ton of use cases. Think about, we've already seen customers who are spinning up a new VCF deployment, for example, and they just want to easily bulk migrate all of the virtual machines from their older environments into that new VCF environment. We have seen customers utilizing this specific capability with VMC on AWS, for example. You can do that as well. So it makes it really easy to migrate virtual machines workloads between vCenter server instances, again, running in different SSO domains. So if we look at workflow 1 to import virtual machines, now you only have to have one vCenter server that is running vSphere 7 update 1C, right? The other one, the source, if you will, can still run 6.7 update 3, 6.0 update 3 and up. So everything in 6.5, 6.7 is all supported, and you can just hit on the newer vCenter server side, import via virtual machines, and what we'll do is take you through this wizard where you can set up a new vCenter connection, or you have a saved vCenter connection. Now, mind you saying that this is a saved vCenter session for this specific user session. So if you re-log into your vSphere client, for example, those saved vCenter servers will be gone. However, it is useful if you're doing multiple migrations, for example. So in this specific, we have set up that connection, and we can just go ahead and select workloads that we need to migrate. In this specific case, I only selected one, but I can easily select more, and off we go. Workflow 2 is the other way around. If you have a virtual machine on a source vCenter server and you hit migrate like you would do with a typical manual vMotion, we now have the new option, which is cross-vCenter server export. Same thing, we set up the vCenters that we need to connect to, and now we can select the compute resource, right? As with typical vMotion. The biggest difference with the Fling and the embedded version in the vSphere client is that we can now do compatibility checks, which we didn't do in the Fling. So compatibility checks obviously there to make sure that the migration will be successful. Also, we can select a different network if we need to. Chances are that on the destination ESXiOS or destination vCenter server in this case, we have a different namings of our port groups. So you can check and select that here. And in the end, you'll initiate a vMotion, but you'll obviously see some information on both the target and the source vCenter server side. So whatever workflow you're using, we see that we now have initiated a vMotion receive operation. And on the sending side, we see a relocate virtual machine. With that, I think we pretty much timed it perfectly, I guess. What I wanted to show you still is all of this information, all about vMotion as well, we put on our new tech marketing home, which is core.vmware.com. We used to have only vSphere blogs, which is still around, but core is definitely the new place to go, not only for vSphere, but everything vSAN and VCF as well. So we're trying hard to consolidate all the information into one place, make it a lot easier for you to find information. With that, I would like to thank you. If you see me on Twitter, if you still have questions left, because we don't have a lot of time to go into that, reach out. Feel free to reach out on Twitter to me or via email, whatever way, and I'm happy to support you with whatever questions. Thank you so much.